All right, we're on question number 16, still in Unit 7, equilibrium. Let's go ahead and get to the question. CO plus 2 H2s yields, that's methanol. The delta H is less than 0, so this is saying that it is exothermic, right? This is exothermic, and if it's exothermic, then heat is a product, okay? All right, the synthesis of methanol and from carbon monoxide and hydrogen gas is represented by the equation above. The value for Kc of this reaction is at 483 K is 14.5. That's just a K that is greater than 1, meaning it has way more products and very little reactants. Which of the following explains the effect of equilibrium constant of Kc when the temperature is raised to this? Okay, so what happens to Kc? So again, you're going to think of equilibrium in terms of Le Chatelier's little seesaw, and you have heat as a product. Well, if I increase the temperature from 483 to 650, my heat will increase. My heat, therefore, will make the seesaw's product side go down. How does it get back to equilibrium? It has to create more reactant. If it creates more reactant, then if you have more reactant, your denominator will increase, lowering your K. All right, so your K will decrease. K will increase, incorrect. K will increase, incorrect. K will decrease, that is correct. Okay, K is constant? No, that's incorrect as well. So the answer, C. C is a great choice. All right, let's go to number 17. Same reaction. Oh, it's actually the same exact question. So, no, it's not. Ooh, this is... Oh, sorry, I went the wrong way. This is not the same question. It's saying synthesis, but it's using the same equation. The synthesis of CHO3 methanol from CO and O2, same details. But now you have a 1 mole sample of CO, a 1 mole sample of H2. In a previously evacuated 2-liter sample, a 2-liter reaction vessel, which of the following is true at equilibrium? So you have 1 mole sample of this and a 1 mole sample of this. Now, just to let you know, think about who's the limiting reagent. That's the limiting reagent right there, because this gets consumed faster. 2 of those get consumed for every 1 that is consumed of the carbon monoxide. Anyways, at equilibrium, oh, okay. So the way I want you to think of this, I have some space to work here. Now again, you're going to set your, like, think of this as a graph. Now, your CO is going to go down by 1. Your H2 is going to go double that, right? And it's going to get consumed. It's going to go down faster because there's a 2 coefficient in front of that equation. So, okay, A says your concentration of your H2 is less than 2 times the CO, or is equal to 2 times the CO. If you double the CO, it's going to be, the H is supposed to be less than the CO, not more than the CO, so A is incorrect. And that's exactly what I just said for the answer to B. H2 has to be less than CO because it is getting consumed faster because of the coefficient of 2 in front. The correct answer, therefore, is B. Ding, 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 ding. All right. Let's take a look at number 18. The synthesis of methanol, same equation going on here, and you have these scenarios. Now, a mixture of the CO and the H2 is pumped into a previously evacuated 2-liter vessel. The total pressure of the reaction at equilibrium. So equilibrium is 1.2 at equilibrium. So what will the total equilibrium pressure in the system be if the volume reaction is reduced to 10 liters? So if you so people are going to think, oh, I have the volume, then I should double the pressure. So you're going to think it's C. However, think about it like this. Think about it in terms of equilibrium. When you decrease volume, right? When your volume decreases, remember, Le Chatelier's stresses, it goes to the side with less moles. Okay, so when you decrease the volume, it's going to go to the side with less moles. And look, there's 3 moles on this side. There's 1 mole on this side. Now, volume doesn't play a part when your equation has equal amounts of moles on both sides, but this has 3 moles on one, 1 mole on the other. Yeah, it's going to decrease in moles. Now, when you decrease in volume, no doubt you're going to increase in pressure. Okay, however, it's also, as you're decreasing in volume, you're going to go from 3 moles to 1 mole. So it won't go, if your, let me put it this way. If your moles stayed the same, if there was a total of 4 moles at the end, like, for every 4 moles, then yes, it would be C. But that is not correct, because the decrease of volume is going to make it move to the right side. If it's going to move to the right side, it's going to become less moles. Yes, the pressure will increase, but it won't double. The answer is B. All right, number 19. CoCl2 yields CO and Cl2. CoCl2 decomposes according to the equation above. When pure CoCl2 is injected into a rigid, previously evacuated flask, the pressure in the flask is initially 1 atm. After it reaches equilibrium, the total pressure in the flask is 1.2. Okay, so I want you to think of it like this. Okay, which of the 19? Okay, so I want you to set it up in terms of an ice table. So you have your CoCl2, and it's going to yield CO plus Cl2. And if you do an ice table here, right, like, you're starting with 1.0 of this. This is 0. This is 0. This is going to be down by x. This is going to be up by x. This is going to be up by x. This is 1.0 minus x plus x plus x. And if it gives you the total pressure, well, this is all the pressures combined. This is equal to 1.2 atm. Now notice this x and this x is going to cancel out, so you have 1.0 plus x is equal to 1.2. In other words, x is equal to 0.2. All right, I'm going to plug these values in. Okay, well, now that I figured that out, here I can get rid of this. And then your values here are going to be 0.8, 0.2, 0.2. Now you're going to do your k. Your k is equal to 0.2 squared over 0.8. 0.2 squared turns out to be 0.04, and that's going to be, I would honestly think a lot of people would make a mistake of making that 0.4, right? So anyways, this is like saying 1 over 20. The answer is 1 over 20. The answer is B. Okay. All right. Let's go to 19. Or no, 20. All right. I'm going to be honest. When you take a test like this and you see a question this long and has all those words and you're just like, what is going on? Like, it's kind of scary. And honestly, these are sometimes the easiest questions. All right. Student 1 has 2 grams. Student 2 has 3 grams. Same mass of water. A little bit more change. No, the temperature was a little hotter, but the temperature changed more here. Okay, chemical reaction happening. I'm looking at student 1. Oh, what's going on here? Okay, now LiCl. If you remember anything about LiCl, Li and Cl are both strong anions, so they disassociate completely. Okay, the Li's go their own way, Cl's go their own way. So why are these Cl's sticking together? That seems wrong. Okay, they should be disassociating into LiCl's like student 1 has it. All right. Two students prepare aqueous solutions of LiCl and measure the properties as shown in the table above. Both students observed that the solid LiCl readily dissolved in H2O. The student drew particle diagrams to explain the changes in the enthalpy and entropy of discussion of LiCl. Oh, that's the key. The students drew these particle diagrams, okay? So obviously student 2 don't know what he's doing because LiCl completely dissociates. Based on the information, the better particle diagram was drawn by which student? Who drew a better diagram? Obviously student 1, because he disassociated the Li and the Cl molecules while student 2 kept them together. All right, so let's see who says that. The answer is A. The better particle diagram was drawn by student 1 because when Li dissolves in water, it dissociates into Li plus and Cl minus, causing an increase in entropy. That is true. Ding, 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 ding. So like I said, that's this huge, long, it's a big diagram. There's this big table. You're thinking there's a lot to this question, and it's like literally the easiest question. 21. Okay, as at 298 Kelvin, ammonium nitrate readily dissolves in water, suggesting that change in free energy delta G favors the dissolution process. However, when ammonium nitrate dissolves in water, the temperature of the water decreases. The particulate diagram above attempts to provide microscopic view of the dissolution of NH4NO3, considering both the change in enthalpy and the change in entropy. Which of the following explains why the particle diagram is able to illustrate and why? Look, I see ammonium nitrate, and ammonium nitrate, by the way, anything nitrate is soluble, meaning it'll completely disassociate. So, okay, they got the ammonium nitrate stuck in the water, some of it came apart, and eventually all of it came apart. Yeah. So what is this showing? The answer is C. The particle diagram is able to illustrate that entropy increases when ammonium nitrate dissolves in water because the ions disperse in the solution. It's showing the breakdown of the ammonium nitrate, which is what it does. Okay. Number 22, you have HCl plus water forming hydronium and Cl minus. Now, this is a strong acid. In 1 molar HCl is nearly 100% disassociated as represented by the equation above. Which of the following best helps explain why HCN, less than 1% of HCN is disassociated? This is a little bit acid-basey, but let's talk about that real quick. Okay, let me just give myself a little space. When you guys do acid bases, Ka, you're still doing products minus reactants. Products over reactants. So when you do something like that, think of it like this. If I have HCl, right? So if I have HCl and it becomes H plus and Cl minus, your initial concentrations in your ice table, if you had an ice table, would be like 100 and 0 and 0. This would go down by x, this would go up by x, this would go up by x. This would be 100 minus, this would go down to 0 because it's a strong acid. This would go up to 100 and this would go up to 100. Now, on the other end, if you had a weak acid, and a weak acid is always like HA, and you're gonna use a double arrow, and that's gonna become H plus A minus. Now, if I did the same ice table and I had 100 of these and I had 0 of these and 0 of these, this is gonna go down by x, this is gonna go up by x, this is gonna go up by x, and I don't know what acid this is, but let's just say this goes down to 70, right? This would go up to 30, this would go up to 30. Now, I'm just using hypothetical numbers, but the point is this: look at the K's. Here, the K, I don't care what that is. It's 100 squared over 0. And you know what 100 squared over 0 is? Is undefined. And you know what undefined is? It's basically infinity, right? Now, the K over here would be 30 squared over 70. And even if it was 70 squared over 30, either way, it's like some number, okay? Point being, look at possible answer choices. On number 22, it says, okay, which of the following best helps to explain why HCN, less than 1% of HCN, is disassociated? Why would it less be disassociated? Well, it all happens to do with this K, products over reactants. I don't know what's doing this, but here, there you go. Products over reactants, right? This products over reactants is so big, it's undefined. The correct answer is C. The equilibrium constant for the dissociative HCN is much smaller. Yeah, it's much smaller. I don't know, even if it was a large number, K of a strong acid, HCl, is infinity. Everything is smaller than infinity, right? So HCN is much smaller than that for the dissociation of HCl. That is correct. The answer is C. You don't have to do all this, by the way. I'm just showing you, demonstrating, and really this is a concept question. So as long as you understand the concept, you can move on without, any scratch on you. All right, number 23, you have a KSP problem here. Ooh, KSP. Okay, so the KSP here, if I had to set it together again, it'd be KSP. Notice I told you about that 4x cubed. This is going to be one of those situations where if you had 100 of these, the Mickey Mouse ears, you'd have 100 of these and you'd have 200 of those, okay? So you would have not just x and 2x, but you would have 2x squared because KSP is going to be products, aqueous and aqueous, but no reactant because that's a solid. So this would be, there's no denominator in KSPs. So this would eventually turn out to be 4x cubed, and we've seen that one time before. A saturated aqueous solution of CDF is prepared. The equilibrium in the solution is represented above in the solution. CD2 plus is 0.0585, F minus 0.117. Some 0. By the way, look at these numbers. This is just this. The F minus is double the CD2 plus. Now you might think, how am I going to do this question? You don't actually have to calculate a number here. You just need to understand that that F minus is double than that CD2 plus because they came from the same source. But some NaF is added to the saturated solution. Which of the following identities the molar solubility of CDF2 in pure water and explains the effect that the addition of NaF has this on solubility? Now think about this. What is Na? Na is a spectator, so it goes away. So really, when you add 0.9 molar of NaF, you're really adding 0.90 molar of F minus. Okay, that's really what you're adding. So if I did, okay, let's, you don't have to do this, but let me explain it. Okay, if you did an ice table, which, again, it's overkill, but I want you to understand the concept here. This is what you have here, and if you have your ice, your CD, we don't care about that, that's a solid. Now you had 0.0585 of this, and you had 0.117 of that, but guess what? When you added NaF, you added a whole bunch of F minus. You added a lot of F minus, right? That's what you did here. Because and again, remember the Na is a spectator, it goes away. Only the F minus sticks around, okay? So what did this do to equilibrium? It made the product side really, 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 really heavy. So how does it get back to equilibrium? It will create more reactant to get back to equilibrium. So answer choice A. The molar solubility of CDF2 in pure water is 0.585. That's true, right? Because, that's what it tells us. And adding NaF decreases this solubility because equilibrium shifts towards the favor of the precipitation of some CDF2. Yeah, if we got to create more reactants to get back to equilibrium, we are going to precipitate some of this solid, and this solubility will be less. Okay, so the answer is A. That is correct. That's a cool question. Okay, main thing you guys got. Okay, you got to be big on whenever you see Na, whenever you see Li, whenever you see K, that you realize that those are spectators. They go away. Okay. All right, number 24. All right. At night, an equilibrium reaction between two different nitrogen compounds generates N2O5 in the atmosphere as represented below, and your K is that really small number. Okay, now this K being a small number means that you're going to have a very big denominator and a very small numerator. So you have very little products, a lot of reactants to get a negative number, a negative exponent there. All right. A mixture of NO3 and a tenfold excess of NO2. So in other words, your NO3 is your limiter. Are placed inside a rigid container at a constant temperature and allowed to reach equilibrium. Which of the following provides a correct comparison of the equilibrium concentration of these species and why? Okay, so do I have more NO2O5 or more NO3 minus? Well, if I have more reactants, then these numbers are much bigger, and the N2O5 is much smaller. So at least this part is correct. So this is incorrect. This is incorrect. At least this part is correct. So it's either A or D. All right, NO2O5 is less than NO3 because K value indicates that the consumption of the reactants is favored at equilibrium. No, the consumption of the production of the reactants is favored at equilibrium. We want more reactants, right? We don't want to consume these and get rid of them. We want to produce them. So this answer is incorrect. By default, that D should say the opposite because a small K value indicates the formation of products is not favored. Yeah, the formation of products is not favored. The formation of the reactants are favored at equilibrium. Correct answer is D. All right. This is a totally strange question. I thought this was like kind of out of nowhere. I was like, what? But it's cool. During the day, solar radiation is absorbed by NO3, resulting in its decomposition. Which of the following best explains whether equilibrium concentration of N2O5 in the atmosphere in the daytime is different than that in the nighttime, and why? Okay, during the day, solar radiation is absorbed by NO3, is resulting in its decomposition. Okay. So, if solar radiation is absorbed by the NO3, resulting in its decomposition, okay, then at nighttime you're not going to have solar radiation, right? So at nighttime, if you don't have NO3, okay, so you got to look at the reaction, right? They're still going back to this reaction. So during the day, here, let me just write that reaction out because it'll make it easier to view it. So we still have this NO3 plus NO2 yielding N2O5. So it's saying during the day, solar radiation is absorbed by NO3, resulting in its decomposition. So in other words, during the day, NO3 leaves. Okay, it starts getting used up. So this happens, right? Which of the following best explains why the equilibrium concentration of NO2O5 in the atmosphere daytime is different than the nighttime? Well, and NO2 during the day is very low because since you get rid of NO3, you create more NO3 during the day. So the NO2O5 goes down during the day. At nighttime, the NO3 doesn't leave, so the NO2 doesn't have to decrease. It doesn't have to decompose. The answer to this question, let's see, number 25 would be C. NO2O5 will be higher at night, yeah. It won't be high. NO2 will be lower during the day. It will be lower during the day. It will be higher at night. It will not be the same at night. No, that's not true. The answer is C. And we really don't care for the explanation either. In the atmosphere, water droplets are suspended in air, forming an aerosol N2O5. N2O5 can form nitric acid under these conditions, as shown in reaction 2 represented below. Okay. So, which of the following predicts the effect of the formation of HNO3 will have on the equilibrium shown in the reaction? Well, okay, HNO3 is on the right side. If you form it, this will happen. If you form HNO3, then what are you going to do? You guys are going to... Wait, what? This is confusing. I see. It says, which of the following products predicts the effect of formation of HNO3 will have on the equilibrium shown in reaction 1? The equilibrium reaction 1 will shift towards the formation of more products because N2O5 H2O5 is removed when it reacts to form HNO3. So yeah, if you start forming more HNO3, it if you sorry, I'm getting confused on my logic here. If you form more HNO3, which of the following effects that predicts the effect that the formation of NO3 will have on the equilibrium shown in the reaction, and why? Well, I'm confused. The equilibrium reaction will shift. The answer is A. The equilibrium reaction will shift toward the formation of more product. Why would it form more product if we formed product? Is that saying that, like, this is the formation of more product? I guess. Because N2O5 is removed when it reacts to form HNO3. Well, yeah, duh. I guess, yeah, the answer is A. That's a little bit too matter-of-factly. It almost feels like there's no question in there, just like a description. So, I don't know. That felt like a little confusing to me. But statement A is saying that the formation of HNO3 is a shift towards the formation of the product. Yes, of course. And N2O5 will be removed because you're creating more formation of HNO3. It's like a little bit too, there's no trick there. So that was a little, that got me confused for a second. Number 27, look at these. You have these two reactions, and look at these KQs. Holy moly. That KQ of the reaction 1 is so big compared to that KQ of the second one. So this means this has a lot more product than reactant, and I should make that reactant even smaller. And then this one has a lot more reactant than product in comparison to one another. All right, the table above shows the data for two reactions carried out in two separated and evacuated 1 liter rigid containers at a constant temperature of 298. To each container, 0.5 mole of the appropriate reactants was added, and the reaction was allowed to reach equilibrium. Based on this information, which of the following correctly compares the relative concentration of BRCl and NO present inside their respective containers at equilibrium? All right. This means if we're going to compare this and this, BRCl and NO, that means this one has a whole lot more BRCl than it does NO, because look, this has a way more product. This has very little product, okay? So first of all, BRCl2 is much higher than the NO. Okay, so it has to be either B or C. All right, let's read B. BRCl is greater than NO, yes, because BR2 and Cl2 are larger molecules. It has nothing to do with their size. Okay, BRCl is greater than NO because the much larger K, EQ for reaction 1 means that much higher concentration of products will be present at equilibrium for the reaction compared to reaction 2. Yes, I like C. C is the correct answer. B is a fail. Number 25. Ooh, look at this. You have iron carbonate and manganese carbonate, and you're looking at the KSP. So this has more product. The top one has more product compared to the bottom one. Let's look at the diagram. You have Fe, and there's all the grays, and then the Fe's are in here, right? You have the MNs, and the MNs are in here, right? These dark ones. Okay. Which of the following explains why the properties listed in the table is best represented by the particle diagram best? Oh, I see. You know what? This is good. Count them. Over here, this has 1, 2, 3, 4, 5, 6. There's 6 FEs. There's 1, 2, 3, 4, 5. Wait, what? Oh, yeah. And there's only 5 in here. In other words, there's only 5 of these. There's only 5 of these, and there's 6 of those. And in other words, it's showing the diagrams, the particular diagrams are showing that the Fe decomposes more, the Mn decomposes less. And that's true because the KSP is higher in the Fe and the Mn is lower, meaning, remember, K is products over reactants. So if you have a higher KSP, that means you form more products. Look, FeCO3 has a higher KSP, and it formed more products. It formed 6 products. So the answer, number 28, is D. The particle diagram best represents the molar solubility is greater for FeCO3 compared to the MnCO3 because it showed 6 things getting broken up, not 5 things being broken up. All right, number 29. When a colorless solution containing Fe3 plus and SCN negative ions are combined, a deep red complex FCN2 plus quickly forms, as shown in the net ionic equation above. Which of the following explains the observation that adding a few additional crystals of KSCN results in the red color of the solution becoming deeper? Remember I said that whenever you see K, you got to think that's a spectator. It goes away. So what is this really adding? It's adding CSN minus. That's what's adding to the equation. So if I add more CSN to the equation, think of your Le Chatelier principle, your Le Chatelier seesaw. That side gets more, the reactant side gets heavier, so you produce more product to get there. All right. The correct answer, A, let's see. The added KCN dissolves, disturbing the charge balance in the solution. Who cares about the charge? Charge has nothing to do with this. B, the added KCN dissolves, causing the solution becomes saturated in SCN ions, which appear red at high. SCN appears colorless, so that is not true. The C, the added KSCN dissolves, causing the reaction system to respond by producing more product. Yes, by producing more product to partially consume the SCN and reduce its concentration. The correct answer is C. Ding, 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 ding. Oh, this one was good. This one was real good. Number 30. Cl2 and H2O yield H3O plus Cl minus and Haeckel. The equilibrium reaction between Cl2 and H2O at 25 degrees is represented by the chemical equation shown above. If a solution at equilibrium at 25 degrees Celsius is diluted with distilled water to twice its original volume, which of the following gives us the value for Q and predicts the response by the system immediately after dilution? The water is doubled. When water is doubled, remember your molarity is concentrated by moles over liters. Well, when you double this, you have your molarity. So looking at this, what if I halved this and I have that and I have this and I have that and I halved all of them? Look at what happens to my KC, or what now becomes my Q. I would have 1/2, 1/2, and 1/2 over 1/2. Now one of these 1/2s and one of these 1/2s go away. They cancel each other out. But now you have 1/4 left over. So what happened to your KC? Your KC is only 1/4 of what it was. The answer, it's either this or this. Let's read them real quick. The Kc and the rate of the reverse action will be greater than the rate of the forward reaction. Remember, K is products over reactants. So now this is incorrect. C is incorrect. The correct answer is D, because the rate of the forward reaction will be greater because you need to create more products to get your QC needs more. Okay, so your QC to become K, can we multiply? Does it make sense if I manipulate this like this? I need to multiply my Q by 4 to get to Kc. So if I have to multiply my Q by 4 to get to Kc, that means I need to increase my products, my numerator. The correct answer is D.